Science fiction writers have long predicted the ultimate advance. A mode of travel so fantastic, our every instinct tells us it can't possibly happen. The ability to transport ourselves instantaneously to anywhere on the face of the Earth or beyond. Teleportation.
All right, guys, just about every single technology that we're using today, inspired by Star Trek, the original from the 1960s. The only thing we don't have today is the teleportation technology. Everything else came to pass. And there's electronics that we have today is much more sophisticated than what they envisioned in the 1960s. Teleportation. Do you think we will ever be able to teleport one place to the next place, Star Trek style? I lied when I said teleportation. We don't have that technology. Actually, we do. The style of teleportation that we use today, using particles, is called entanglement. It's not the Star Trek style. I'm talking about Star Trek style. What is the Star Trek style? You take a person and you take this person and break this person into its atoms and molecules and turn it into a particle beam. And then send this particle beam to a given location and reconstruct the person back up from atoms and molecules into the person that the person was. All right, do you think we will ever be able to do that? All right, guys, I got news for you. This is the sort of stuff that happens to you, believe it or not, except it takes about 7 years. You're not the same person as you were 7 years ago. You don't have the same atoms and molecules. Everything gets recycled in your body. All right, the atoms and molecules making up your cellular structures are not the same atoms and molecules, except you quicken that process. All right, I will strip you into your atoms and molecules. I will break you down into your atoms and molecules. Instead of taking 7 years in terms of rebuilding you, I'm doing it within a fraction of a second. So what is the argument against that? Do you think we will ever be able to have this sort of technology? We'll find out. Take a look at this picture. Is this a he or she? And why do you care? Well, look at the details. Oh my God, look at the details. You can get this kind of this sort of details using a microscope. It's not the regular optical microscopes. This is an electron microscope. By using electrons, actually, you can come up with this kind of details, but which means that the electrons must be behaving like waves. Particles, could they ever behave like waves? We never will get to investigate. All right, this link is not going to work, but let's move forward. Grease, the movie Grease. What does the movie have anything to do with the quantum theory? Andrew Cleland's. So as soon as you see something like that, you go, oh, this is the many worlds interpretation.
And begins to oscillate between these two realities.
Which means that there are two possibilities, and both possibilities are taking place at the same time. And notice that that's one interpretation. That's not the only interpretation. The second interpretation.
And because it's not predicted, it's not something we can test. So that's generated to try to explain this. One of them is the many worlds interpretation.
All right, so where do we get the many worlds interpretation from?
Parallel universes. But in the end, those are not predictive. And because it's not predicted, it's not.
The other one is the Copenhagen interpretation.
There's a number of different interpretations that have been generated to try to explain this. One of them is the many worlds interpretation or parallel universes. But in the end, those are not predictive.
And the other one is the Copenhagen interpretation. So where do we get those interpretations from?
You're watching a Nova Video podcast.
Like that, moving around.
Particles dissolving into waves. Waves of what? All right, guys, this is Bose-Einstein condensate. State of matter near absolute zero. Particles will dissolve into waves. Waves of what?
Really difficult for me to explain just why that is, but that's the way it is. They're everywhere. This little wave packet over here, can't tell whether it's this one or that one or that one or that one or that one.
And then the particles will start to appear at multiple locations.
It's there, it's there. Running around gaily, freely, bouncing into things, sometimes going fast, sometimes going. There's nothing else like that in physics, and certainly not in human experience. So just to think about am anymore, I'm at rest, and all the other atoms gaily, freely, bouncing into things.
And then your absolute zero, the atoms will slow down.
Sometimes going fast, sometimes going slow. But on the Bose condensate,
and then next thing you know, the same atoms will appear at multiple locations.
Everywhere at once. I've lost my identity. I don't know who I am anymore.
And there's also a statement in the documentary that says absolute zero could never be reached because the last bit of energy would take forever to remove from that system. So why is it that when the atoms start to slow down, they will appear at multiple locations? Where do we get that understanding from? And why is it that the physicists are so certain that you could never reach absolute zero? Because the last bit of energy would take forever to remove from the system. Okay, so going back to the same question. Light, composed of particles or waves? Newton said it was composed of particles, and Huygens said it was composed of waves. Initially, we decided that Huygens was correct. What do we know today? Today, we know that it's both, right? Depending upon the experiment, it can act like waves or it can act like particles. So the question was, and this is something that Einstein was thinking in 1917 or 18 as he was working on his theory of gravity. I was thinking that, can we make the same argument regarding these particles? I mean, electron, no one has seen an electron before. So can we make the argument that the electrons may also have a dual nature? About atoms, about molecules? Is it possible? He was thinking about it on the side, but he didn't really put anything on paper. About the same time, this guy in the background was thinking about the same thing. All right, so this is the guy. What's his name? All right, in the United States, depending upon who your professor is, his name is either de Broglie, and you pronounce everything in sight, pronounce the shit out of everything, or acknowledging that this guy is French, you may go, okay, so I know there's some silent letters here and there, but you don't know which ones because you're not French. Only the French know which ones. French usually put half of their alphabet in every single word, and they're the only ones to know which ones to skip. All right, so you would say de Broglie. All right, so that's a bit of an acknowledgement that this is French. And who would have guessed that his name is de Broglie? All right, so that's French for you. Weirdos. All right, so this guy is working on his PhD dissertation, and is pondering about the same question. Is it possible that these particles also have a dual nature? Is it possible that they can act like waves? These particles can also act like waves.
A century earlier, Thomas Young had proved light travels in waves. Was it now going to turn out that light is really made of particles after all? Perhaps this whole business of particles and waves was in need of an entirely fresh perspective. Louis de Broglie got a history degree en route to a career in French government, a fresh approach to physics if there ever was one. Maybe that's why, in the 1920s, he was the one to ask a crucial question. If light waves can be particles, is it possible that particles, such as electrons, can also be waves?
All right, so let's talk about his background a little bit. Number one, this guy's a prince. And if you ever wonder why all the royalty look alike in Europe, because they are related, they're like family members. They are like family members. Most of them are cousins, distant cousins. And for whatever reason, most of them have horse faces. I don't know why. So this guy is royalty. He's got a background, not in physics. His background is exactly the same as Ed Witten's background. History. It's got history or anything to do with physics. Nothing. This guy is an outsider. So he's pondering. Is it possible that given the fact that light has a dual nature, can we make the same argument regarding particles? Is it possible that they also have a dual nature? Particles, could they have a wave nature as well? This is the sort of stuff that only an outsider can ask, because no physicist would take something like this seriously. So this is his doctoral dissertation. They've been working out for 2 years. And then he's about to publish it and defend it. And that's the question that he's trying to resolve. All right, take a look at the first equation up. You got the wavelength on the right, Planck's constant, divided by P. This P is known as momentum. This is my Ford Tempo moving at 60 miles per hour. You got your speed, and you got the mass. And P is known as momentum. Momentum is an early way of saying motion in a given direction. What is it that I'm looking at and not liking? Everything. Everything is bullshit. I look at it, I say, holy shit, I can't believe this guy actually got away with this for 2 years. And I just feel like I want to kill someone. And I have to listen to this guy talk French and say, blah, 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 blah. I just want to grab him and then squeeze the shit out of him. I want to kill this guy at this point because he's about to waste my time. And I'm really angry with his advisor for letting him get away with this bullshit. What's the problem that's really pissing me off? Wavelength means that there's a wave associated with the motion of my fucking Ford Tempo. There's no such thing. Wave of what? This is my Ford Tempo moving at 60 miles per hour. It's creating waves. Waves of what? There's no such thing. There is no such thing. At that point, I would just put a stop to it. I would say, what is this? What is this the wave of? It's going to say, well, blah, 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 blah. This is your Ford Tempo moving at this. Just shut the fuck up. All right? You can't explain it. And that immediately gets into trouble. Immediately. This guy opens his mouth. At that point, he's in deep water. He's not going anywhere at this point. All right? He's a fair game at this point. You skin this guy alive. This is complete fucking nonsense. At that point, it's just a game ender. Because you can't explain this. Wave of what? This is literally a mass moving at this speed would not generate waves. There's no such thing in physics. Complete nonsense. Who else knows that this is complete nonsense? His advisor does. His advisor does, because what this guy did, he takes Einstein's equation up, mc squared, and combines it with the photoelectric effect. And somehow through mathematical manipulation, I don't know why it takes him 2 years, he comes up with this. That's not how physics is done. These symbols mean something. You don't just play with the symbols and come up with an equation and say, this is my PhD dissertation. Only a guy who's not a physicist would do something this stupid. So his advisor sends the advanced copy to Einstein. Einstein looks at it. He says, oh, you guys are French, you wouldn't be able to get this. De Broglie is correct, so just give him his PhD. Next time when I'm in France, I'll explain it to you guys. If Einstein is in agreement with you, obviously you don't question it. So the PhD board are really pissed, but they say, hey, Einstein likes it, so we're not going to question it. Why did you come up with it? What are you thinking? What's your understanding of it? Because this explanation is complete bullshit. All right, this explanation does not work. He was never able to explain this shit. He says, oh, here's what I'm thinking. Remember the standing wave patterns, both ends are fixed, and remember the fact that no one knew how to explain the Bohr orbitals, where these orbitals come from. He says the electrons, by their motion, they create these matter waves. He says, I don't know what these matter waves, but the motion of the electrons, the momentum, mass, and the speed generates these matter waves at locations around the nucleus, where the matter waves form these perfectly circular orbitals. That's where the orbitals will happen. Guess what? When you plug the numbers in, damn, you end up getting Bohr orbitals. And all of a sudden, assuming that the electrons generate these matter waves and at locations around the nucleus, these orbitals form perfectly circular standing wave patterns. That's where the orbitals are. Beautiful. Now it works out. Now everyone is interested. No one gets the idea behind it, but the electrons, by their motions, generate these matter waves at locations around the nucleus where they form these perfectly circular orbitals. That's where the orbitals are. All right. So this is Einstein saying, hey, just go easy on him. As far as he was concerned, de Broglie's theory was correct. He said, you guys won't get it, but I'll explain it later. So Einstein put his support 100% behind it. So the next question is, how do we know the existence of these matter waves? How can we test for them? Well, how do you test for the existence of waves? Remember the double slit experiment, all right? You will have to look for an interference pattern. So he said, if you get the electrons to move roughly about 10 million miles per hour, all right, they would generate these waves whose wavelengths would be comparable to the wavelengths of light going through a double slit. So which means that you would see some kind of an interference pattern. All right, the spacing between the atoms is comparable to the wavelengths of these matter waves. So by using spacing between the atoms, they end up using this metal foil, and then they send these electrons through them. Okay, the X-rays that you're looking at, fast-moving electrons, and then sure enough, it causes these interference patterns on the wall, on the screen. All right, so this is the electron diffraction pattern, the interference pattern. This is the X-ray diffraction pattern. Notice that the electrons end up causing a diffraction pattern, which is much clearer, much higher resolution. That the guy who ended up doing the experiment, his name is George Thomson, ends up winning the Nobel Prize in 1937 for proving that the electrons also have a wave nature, because the electron matter waves also interfere just like light does. But happens to be the son of J.J. Thomson, who discovered the electron. So J.J. Thomson ends up winning the Nobel Prize in 1906 for proving that electron is a particle. In 1937, his son wins the Nobel Prize for proving that the electron also has a wave nature. Same family, 2 Nobel Prizes, and same topic, the electron. So what does it mean? So not only de Broglie gets his PhD, also wins the 1929 Nobel Prize for discovering the matter waves. So what are these matter waves? We'll discuss that. The only thing I'm going to say is electron microscopes do use matter waves, and by using matter waves, look at the resolution. This is Vacro, guys. Look at the resolution. Unbelievable. By using the wave nature of electrons, which happens to be known as the matter wave of the electrons, you can come up with the resolutions which are unbelievable. We get that statement from. All right, J.J. Thomson discovered the electron. Just remember, guys, it's a point particle. It's got a measurable charge. It's got a measurable mass. Millikan is the guy who measured the charge as well as the mass of an electron. All right, Ernest Rutherford is the first person who actually came up with the model of an atom through some scattering experiments. Hydrogen atom is the one that they were focusing on. It's got a size, that's the radius, half an angstrom. And then on top of that, it's got an ionization energy. That's the amount of energy required to knock an electron out of the atom. Electron moves about the nucleus inside this atom, like the way the atoms move about the sun. Except this model didn't work out too well, because the electron, orbiting the nucleus, because it's accelerating, it would radiate all of its energy within a fraction of a second. This says 100 millionth of a second, and collapse into the nucleus. All right, so this atom, this theory did not survive. And then Bohr comes along. He gives us a stationary atom. All right, so he says, oh, you got these orbitals within which the electrons can move without radiating energy. And they can jump by absorbing and re-emitting energy between these orbitals. All right, this worked quite well because, number one, it gave us the correct ionization energy of the hydrogen atom. And on top of that, it gave us the correct radius, the size of the atom. So here's the ionization energy. On top of that, it was able to explain the spectral lengths of the hydrogen atom. It was able to explain why the sky is blue. It did a lot of good. And then he won the Nobel Prize in 1922. All right. The problem with his theory is it had a bunch of made-up rules. So those rules succeeded in explaining hydrogen atom. You could not generalize the hydrogen atom into any other atom. So at that point, we completely got stuck. And then de Broglie was able to explain at least one of the mysteries about the hydrogen atom, because no one knew where these orbitals were coming from and how the electrons knew where they were. So he came up with the matter waves. So the matter waves are waves created by the motion of matter, like the electrons. So the electrons do have matter waves. Its locations, they form perfectly circular, and this is a circular standing wave pattern. That's why the orbits were happening. And notice that this is not a perfectly circular one, so there's nothing happens there. But this is perfectly circular. And all of a sudden you go, wait a minute, this is weird. The reason why this is weird, all of a sudden you kind of question whether electron is a particle or a wave. All right, so de Broglie was talking about matter waves, and all of a sudden you go, wait a minute, where is the electron within this wave, and how is this wave coming about? They knew for a fact that this thing was real because the only thing you have to do is you have to form these diffraction patterns. The diffraction means interference patterns. The waves interfere constructively or destructively. At locations, you end up getting a destructive interference pattern, so it's going to be dark. At locations, you end up getting a constructive interference pattern. It's going to look bright. So there's something. It's some sort of waves that the electrons are generating. They act like waves. Okay, so the matter waves. We don't know what they are, but they are there. And then you get these diffraction or interference patterns out of it. So the guy who proved this is George Thomson, who wins the Nobel Prize in 1937. Happens to be the son of J.J. Thomson, who discovered electrons. So 2 Nobel Prizes, same family, same topic, electrons. All right, and then you got the de Broglie, not only gets his PhD, but also wins the Nobel Prize in 1929. So the question now is, what the hell is happening? Electrons, are they waves or particles? Okay, with light, there was a compromise. Depending upon the experiment, the physicists decided that light can act like a wave or a particle. What does it mean? It doesn't mean anything. Conceptually, you can't wrap your brain around it. So depending upon the experiment, the light can take either form. So the question is, can we make the same argument regarding particles? Can we say that the particles also have a dual nature? Depending upon the situation, is it possible that they act like waves or particles? So that becomes the question. So they couldn't quite make that argument. They couldn't get to that point. It wasn't immediate. And then this guy comes along. His name is Heisenberg. Those of you guys Breaking Bad fans, you will remember Walter White being Heisenberg. And Walter White was a chemist, obviously. Chemistry is applied quantum theory. He's still Heisenberg's name. Heisenberg is one of the biggest names in physics. All right, Heisenberg is an interesting character. Number one, he solves the problem that Bohr was working on. And he was able to solve it because he was already working for Bohr. At the time, he hated Bohr's theory. The reason why he hated Bohr's theory is because Bohr's theory is extremely visual. And you cannot see inside of an atom. So why come up with a visual theory? Heisenberg thought to himself. I mean, you literally cannot see what's going on inside the atom. We don't have a visual conception of what takes place inside the atom. So why worry about coming up with something visual? Why not just focus on what you get out of an atom? So what do you get out of an atom? Yes, from every single atom, we get these spectral lines. Right? Remember, hydrogen has 4 spectral lines. Sodium is going to have a number of spectral lines, and that every single element has different spectral lines. Now, when you're looking at these spectral lines, you will notice that not only all of them have different frequencies, which means that they have different colors, but they also have different intensities. So he gathered the frequencies and the intensities of lights, spectral lights, coming out of each and every single atom, and then he organized them into tables, and he started to look for patterns. And then eventually he found those patterns. Okay, so he came up with something called the matrix mechanics in 1925. 1925, he was born in 1901, so he's 24 years old. At the time, he solved the biggest mystery in physics. This guy is only a few years older than most of you guys. At the time, he solves the problem. So he takes everything and then he puts them into these tables. He organizes everything into tables. He starts to look for relationships. And then eventually he realized that there are some relationships. There's some kind of a hidden mathematics that he discovers in organizing these tables. This is what I'm talking about. These are the tables that he's talking about. So he got a bunch of numbers, he multiplies them, and then he gets a bunch of other numbers, and then he starts to look for relationships. And all of a sudden he discovers that there's some kind of a hidden mathematics that just pops out of it. And then he gets all excited, and he discovers this during a vacation. So right after his little discovery, he comes back, and he's not entirely sure if he wants to publish it as yet, because he discovers a sort of math that he has never seen before. So he finds this guy, and this guy is another genius. This guy's name is Pauli. Those of you guys who've taken chemistry, you will probably recognize him. It's got something called Pauli exclusion principle. Pauli was a well-known name in physics at the time because he was a child prodigy. When he was 16 years old, he decided to reformulate Einstein's theory of gravity. Remember, Einstein worked on this theory for 10 years. Pauli was able to redo Einstein's theory of gravity from scratch within a few months when he was still in high school. Even Einstein was impressed. This kid was able to do what took Einstein 10 years on his own without using any documentation and then he was able to replicate Einstein's work, and he was only 60 years old. Needless to say, by the time Pauli was 21 years old, he had his PhD in theoretical physics. Now, if you were lucky enough to be good friends with him, you would talk to him before publishing a paper. And if you said, hey, trash it so that you don't embarrass yourself, you would trash it, and he would say, publish it, and then you would get the Nobel Prize. All right, so this guy is some kind of an arbiter of the quality of the papers coming out of his friends, basically. So Heisenberg, they're really good friends. So Heisenberg, not quite sure what the hell he came up with. So he takes his papers to Pauli. He says, Pauli, should I publish this? I don't know what I'm looking at. I discovered this in mathematics. And it somehow things appear to be working out. I'm not sure how to evaluate this and whether or not I should actually publish it. So Pauli says, okay, Olivia, take a look at the paper. I'll get back to you soon. And Pauli is looking at it. He doesn't know what he's looking at. He's never seen that sort of math before. To his credit, he takes his paper to his boss. His boss is Max Born, or Max Born, because this guy is also German. And his boss is a mathematical physicist. And he's looking at it. He says, oh, I remember doing this sort of math. He says, when I was an undergraduate student. And then he realized that this is linear algebra. This is the sort of algebra that today you would learn this sort of stuff in high school. He said, oh, this is simple. Evidently Heisenberg, without noticing, he reinvented linear algebra. He says, Pauli, if you don't know how to use matrices, if you don't know how to use linear algebra, just go study it and then check to see if this theory makes any sense. Pauli, being a genius that he is, it probably takes him less than an hour to master linear algebra. And then eventually they start applying Heisenberg's matrices. Those tables are known as matrices to different elements in chemistry, in atomic physics. And sure enough, theory works out beautifully. By the way, guys, Max Born happens to be the grandfather of Olivia Newton-John from Greece. Remember, this guy is German. Olivia Newton-John is from Australia. How did that happen? Oh, remember, a lot of the physicists end up losing their jobs because Leonard became an advisor to Hitler. Max Born was one of them. So he was lucky enough to leave Germany, so he went to England, and obviously his kids ended up moving to Australia, and eventually the movie was made, and Olivia Newton-John became real famous. So that's the story behind it. So Max Born says, hey, these are matrices. Boom, boom, boom. Supply matrix algebra. Let's check to see things work out. And this is Pauli, and then Pauli works it out. And then Heisenberg gets back to him a couple of days later and says, so he says, what should I do? Should I publish it? Is there any validity to this work that I've done? And Pauli says, oh, gee, he says, not only your theory works, it works beautifully. It's finally, you came up with the generalized model of the atom. Okay, so whatever you came up with, the matrix model worked. So matrix model gets published, and the mystery of the atom is solved. He wins the Nobel Prize in 1932. Oh, by the way, I gave you the Disney version of it. The mystery of the atom was not solved. The only thing which was solved, now we had a mathematical model that agreed with the experiments. Matrix model does not give you any insights into what goes on inside the atom. All right, somehow he captured the mathematics of it, except the mathematics is just so abstract and so thick, you cannot get to the physics of it. All right, so there's one-to-one correspondence between the mathematics as well as what takes place inside the atom. But the mathematics does not open the curtains for you. You have no idea what's going on inside the atom. So that became a huge problem for physicists, because the whole idea of physics is trying to understand what's going on, and there's no way you can understand what's going on inside the atom. All right, so why didn't Heisenberg like the Bohr's visual model of the atom? Because you cannot visualize inside the atom what's going on inside the atom. You cannot see what's going on inside the atom. So why come up with a visual model? Trying to come up with a visual model only constructs the theory. So what was the problem with what was the problem that Heisenberg trying to solve? He was trying to come up with the he was trying to come up with the generalized model of the atom. Was he able to solve this problem? Absolutely he did. And it worked out beautifully. But the problem is, did Heisenberg's model provide any insights into the workings of an atom? No, nothing. They came up with a model that agreed with the experiments, and because it's not a visual model, now we have no idea what's going on inside the atom. So we were still stuck. Physics was still stuck. It couldn't go anywhere. And then here's what happened. This guy comes along, Schrödinger. All right, you guys will recognize him by his cat. Remember to say his cat. Schrödinger he's an Austrian physicist, theoretical physicist, and he passionately hates Heisenberg's theory. And not only does he dislike Heisenberg's theory deeply, he also does not like Heisenberg. These two hated each other. The reason why he didn't like Heisenberg's theory is because Heisenberg's theory does not provide any insights into the inner workings of an atom. He cannot get to it. And Schrödinger, at the same time, he's married, but he's a womanizer. All right, this is where things get really interesting. This is 1924 or something, I think Christmas time. So he checks into a hotel with whom we have no idea, girlfriend, prostitute. I don't know. We don't exactly know what's going on. The only thing which is going on in his mind is he's thinking about the de Broglie matter waves. All right, so he's kind of curious about the de Broglie matter waves. So de Broglie matter waves, electrons, are they particles or are they waves? We've never seen an electron before, he thinks to himself. Why do we assume that the electrons are particles? Why not assume that they're just waves? Why not assume that the atoms are just three-dimensional standing wave patterns? Why not assume that the molecules are just three-dimensional standing wave patterns? But he's trying to figure out how he wants to do this stuff in his mind, and at the same time he's engaged in this sexual act. I don't know which position they are in. They're waving back and forth while he's thinking about the particles and waves. And then all of a sudden the inspiration hits him. The inspiration that hits him is, oh, wait a minute, just ignore the particles. Just assume that everything in the atomic scale is a three-dimensional standing wave pattern. All right. And then shortly after that, after the inspiration hits, it takes him a few weeks to actually formulate everything. He came up with these matter waves. Now these matter waves become the Schrodinger waves. So de Broglie-Schrodinger's waves, de Broglie's matter waves become Schrodinger's waves. Sets up the mathematics, and then tweaks the mathematics until the math gives him some numeric predictions. And sure enough, these predictions 100% match the hydrogen atom. And not only these predictions match the hydrogen atom, it also matches every single atom known to man. That he also discovers the generalized model of the atom, for which he is also awarded the Nobel Prize following year, which is 1933. All right, guys, both the wave model, Schrodinger's wave model, and the Heisenberg's matrices were discovered in 1925. Both of them are competing with each other. Heisenberg's model provides no insights into the inner workings of an atom. Schrodinger's model is highly visual, except the atoms, the molecules, the electrons, all made up of waves. There are no particles at that level. All right, so what was the problem that Schrodinger was trying to solve? He was also trying to come up with the generalized model of the atom, but he was trying to come up with a visual model of the atom. According to the Schrodinger's wave model, electron, wave, or particle, electron is a wave. It's a three-dimensional standing wave pattern. So is an atom, so is a molecule. Everything at that level are three-dimensional standing wave patterns, and of these matter waves, so to speak. So literally, the matter dissolves into waves at that point. It forms electrons, it forms atoms, it forms molecules. All right, so matter waves are made up of matter, in essence. And these matter waves are the ones magically collapse into, oh, their experiences, particles. It doesn't have an explanation for how that comes about. So what are the shortcomings of the Schrodinger's wave theory? All right, let's finish this portion up and then go take a break. Shortcomings of the Schrodinger's wave theory is fairly obvious. It does not explain any phenomena that requires quantization. You cannot use Schrodinger's wave model to explain the photoelectric effect or black body radiation. And it doesn't explain why the electron appears as a particle. It's got a measurable mass. How can something have a measurable mass if it's not a particle? It doesn't explain how electron has a measurable charge. If it's not a particle, it cannot have a measurable charge. And all of a sudden Schrodinger realizes that despite the fact that he had a working theory and there were waves within atoms, he couldn't understand exactly what these waves were or what they were doing. All right, so all of a sudden this theory also ended up running into trouble. All right, guys, take a break for 10, be back in 10.
You're muted. We can't hear you.
Yeah, at the heart of the quantum theory, you got the Heisenberg's uncertainty principle. Give yourself 5 points for that one. It's really simple and commonsensical. It goes like this. All right, so the electron makes a jump. It's in a high energy state. All right, if you are looking at it right now, do you know where the electron is? Of course you do. Where is it? Right here, guys, right here. All right, right here. This is where the electron is. Now that you know exactly where the electron is, do you know which direction it's moving? Notice that that information is lost. If you know the precise location of the particle, you have no idea what the particle is doing. The particle is either going to be going this way or that way. You have no idea which direction it's going. You have no idea how fast it's going. So that information is lost. Notice that the particle is doing a transition at this point. Now you know precisely what the particle is doing, but do you know where the particle is? Do you think it's located here? Do you think it's located here? Do you even know for a fact that this is the path that it took? Notice that that information is lost. So all of a sudden, Heisenberg discovered that there's no way you can know where the particle is and what the particle is doing at the same time. That's known as the Heisenberg's uncertainty principle.
The essence of the Bohr-Heisenberg picture was that the electron was a particle. However, there was a certain amount of uncertainty with regards to where the particle was. Now, one day, Heisenberg was so paralyzed, worrying about all these problems, that he took a walk in the park. Outside his institute, there's a famous park, and late at night, he walked through the park wondering, how can it be? How can it be that you don't quite know where the electron is? And then in a flash, he understood. Because to understand where an electron is, you have to look at it. To look at it, you have to shine a light on it. But when you shine a light on it, that disturbs where the electron is. So the very fact of observing an object changes its location. Therefore, he realized that uncertainty is an essential part of his picture.
Heisenberg calls his insight the uncertainty principle. In a clear mathematical way, it says the more you know about a particle's position, the less you can know about its speed and direction. And the opposite is also true. The more you know about a particle's speed and direction, the less you can know about where it is at any given time.
All right, active observation influences the quantum system. Try to follow the dots. You see where the dots are. As soon as you look at it, it vanishes, right? All right, that was the original interpretation. Active observation influences the quantum system. You cannot know where the particle is and what the particle is doing at the same time. You cannot know the location and momentum, the motion at the same time. That's what it means.
When I walk by, people be giving me the Nobel Prize. Biggest things in Schrödinger's cat, the milk water in his hat, yeah. This is how I roll. I put the party bucket particle. It's about uncertainty. My principle just can't be beat, yeah. Girl, look at those quanta. Girl, look at those quanta. Girl, look at those quanta. They disturb. Girl, look at those quanta. Girl, look at those quanta. Girl, look at those quanta. They're disturbing. I measure a quarter now. This is what I see. I get the exact location, but not velocity. I find physics in my brain, and I think the right to show it. Show it, show it, show it, show it. It's quantum, I can't know it.
As soon as the particle makes a transition from a higher state to the lower state, because of the Heisenberg-Sandstrom principle, the light is being emitted.
It's quantum, I can't know it. Yeah. This is my equation. Helps explain.
All right, let's focus on the equation because my iPad is not connecting. All right, so number one, this is done by one of my students, The person that had done their project, that's actually a she. She ended up modifying her voice completely. And she's actually a graphic design major. I'm surprised how well this project turned out. Not surprisingly, she's a Canadian and she's currently working as a stand-up comic. So this is actually cute. All right, guys, the X represents the uncertainty regarding location and delta P represents the uncertainty regarding motion, momentum. That's what it means. All right. So if you know the location precisely, and when you know the location precisely, uncertainty regarding location goes down. All right. So which means that the uncertainty regarding position, momentum goes up. All right. So if you know precisely where the particle is, you have no idea what the particle is doing. Okay. So that's the interpretation, the generalized interpretation. All right. Now let's change the interpretation around. Near absolute zero, what do you think is happening? Near absolute zero, the particles are slowing down. All right. They're slowing down to stop. So the uncertainty regarding motion goes down near absolute zero. So which means that they're slowing down, which means that there's no uncertainty, they're stopping. So what happens to their location becomes uncertain. So the same particle is going to start to appear at multiple locations. That's what it means. There's a second form of the same equation, uncertainty equation. That says the uncertainty regarding energy and the time still has to equal to or larger than h bar. H is the Planck's constant divided by 2. H bar is h divided by 2 pi, so everything is divided by 4 pi. It's not that important. All right, so what that means is near absolute zero, particles will slow down. All right, so which means that their kinetic energies will start to go to zero. So the uncertainty regarding their energy diminishes, which means that the uncertainty regarding time is going to go up. So what that means is the last bit of energy will take forever to remove. All right, so when the uncertainty starts to go to zero here, time becomes infinitely large. Hence the reason why physicists will argue that the absolute zero can never be reached. All right, so these are the arguments regarding that. Heisenberg's uncertainty principle. So regarding the Heisenberg's uncertainty principle, all right, so when you start to approach absolute zero, what happens? The uncertainty regarding motion diminishes. Uncertainty regarding location increases. So the same particle, you will see the same particle at multiple locations. In fact, you will get to see the same particle at every single location where it could possibly appear. As a result, it's going to look like a wave. All right, so that was the Bose-Einstein condensate. That's the picture of Bose. All right, something about the Heisenberg's uncertainty principle. So it would be impossible to reach absolute zero because the last bit of energy would take forever to remove from the system. So you don't have forever to remove the last bit of energy. That's the reason why absolute zero can never be reached.
In many a science fiction film, you don't need a vehicle to get around.
And because of the Heisenberg's uncertainty principle,
Energize.
Star Trek style teleportation might be impossible. Because for you to be able to teleport someone, you need to be able to map the location of every single atom and molecule making up the human body and know exactly what these atoms and molecules are doing at the same time and be able to reconstruct it at a given location after you turn that person into a beam of atoms and molecules.
The most famous Star Trek gadget.
Heisenberg's uncertainty principle will not allow you to be able to map the exact location and exact motion of these particles at the same time.
Of them all, the transporter. It reduces a person to atoms, zaps the atoms across space, and reassembles them somewhere else.
The reason the transporter, by the way, was created in Star Trek was that Gene Roddenberry simply didn't have the money in the early episodes to show a spacecraft landing, because the visual effects cost a lot of money.
Unfortunately, says Krauss, the transporter is probably the one piece of science fiction we'll never see.
It's due to a fancy law of physics called the Heisenberg uncertainty principle, which says that in principle even, not just in practice, but in principle, I can never know where every atom is in your body and precisely what it's doing at the same time.
So what rematerializes at the destination is only the transporter's best guess of you. And we've seen what happens when atoms get mixed up in transporters. But the technical issues of a transporter pale in comparison to the ethical ones, says Krauss. Are human beings the sum total of their atoms? How do you transport a soul? It's those kinds of questions that even the best science and science fiction will have a tough time tackling in the coming century. Jack Smith, ABC News.
Einstein's static universe takes a beating by the quantum theory, by the Heisenberg's uncertainty principle. Guys, the reality is made up of atoms and molecules. Atoms and molecules obey the Heisenberg's uncertainty principle. If the future, the past, the present all exist, they cannot exist in one single static form, because the atoms and molecules cannot occupy a definite position and motion. So the future cannot be fixed, the past cannot be fixed, and the present cannot be fixed. If Einstein's theory is correct, which it is, according to the quantum theory, the future, the past, the present must be happening, all their possibilities. Every single possibility must be happening at the same time. That's what it means. So if you could just do time travel back to the past, if you just wanted to go to yesterday, if you just wanted to go to an hour before or a minute before, you would not be going back to the place where you came from. That's what it means. All right, if the future, the past, the present all exist at the same time, all the possibilities must exist at the same time. This is the quantum leap. According to the Heisenberg's uncertainty principle, you cannot have a one single static universe. That's what it means. And all of a sudden we have the possibility of time travel. All right, so next question is, particles are waves. So electrons are particles, the atoms are particles, the molecules are particles. So the question is, Schrödinger waves, what are these waves of?
Which is it? Is matter made up of waves or particles? They seem to be complete opposites. Waves can pass through one another, sometimes canceling each other, sometimes making even bigger waves. But particles, on the other hand, bounce, smash, exert force when they meet. They can't cancel each other out.
So these two pictures clashed with each other, and they debated, and they had arguments, and they yelled and screamed at each other. In fact, one day, Heisenberg was so worried that he simply came down with hives and hay fever and tremendous case of allergies, worrying about whether or not the rival picture was correct.
In 1926, Bohr and Heisenberg invite Schrödinger to Bohr's new institute in Copenhagen to try and work out their differences. Heisenberg writes about the visit.
Though Bohr was an unusually considerate and obliging person, he was able in such a discussion to insist fanatically and with almost terrifying relentlessness on complete clarity in all arguments. He would not give up, even after hours of struggling, until Schrödinger had admitted that his interpretation was insufficient. Every attempt from Schrödinger's side to get around this bitter result was slowly refuted, point by point, in infinitely laborious discussions.
Bohr's wife nurses Schrödinger when he falls ill from exhaustion. She brings him tea and cake, even as her husband sits on the edge of the bed continuing the argument. Still, Schrödinger clings to his classical view, wearily noting at one point, if one has to go on with these damn quantum jumps, then I'm sorry I ever started to work on atomic theory.
So the question remains, matter waves that De Broglie came up with, that later became the Schrödinger waves. What are these the waves of? What do they represent in physics? The answer came from this guy, Max Born, granddaddy of Olivia Newton-John. He said, hey, these waves simply are probability waves. That's it. There are particles, and then you got these probability waves, and these probability waves will guide the motion of these particles. Everything regarding the position, as well as the motion of these particles, will be embedded mathematically within these waves. That's it. It almost becomes like a computer program, so to speak. It's a weird interpretation. And why is it that we decided to settle on this interpretation? You'll find out shortly. It's weird. According to Bohr's theory, electron occupies a definite position. The atom has a definite radius. That's half an angstrom away. All right, and then with half an angstrom away, you got this orbital. Within this orbital, the electron is free to move this way or that way. That's it. This was the planetary model rescued by Bohr, and then it kind of worked out. According to the Bohr interpretation, most likely location based upon the Heisenberg's uncertainty principle, is electron is most likely half an electron away. It's not a definite statement. Most likely, it could be anywhere else. It's easy as you could tell, but this happens to be the most likely location. So the next question is the electron moving this way or that way? There's no such thing. The most likely location, electron just appears and vanishes at that location, and that becomes an atom. All right. So what does that look like? It looks like this, guys. This is known as the probability cloud. And finally, they were able to probe into the electron. They were able to probe into the hydrogen atom. 2013, this is 7 years ago, and they were able to construct a picture of this. Is a construction. This is an experimental visualization of what they were able to find. And notice that the snapshot of what the inside of an atom looks like is identical to the Bohr model, which is otherwise known as the Copenhagen model of the atom. It's identical. All right, so all of a sudden you have these probability clouds. All right, so probability cloud is going to tell you about the most likely location of the electrons. And notice that the electron cannot be here. It cannot be here. Most likely location is going to be at the surface of this globe that you're on. Or this is a probability cloud of a different sort of setup. Once again, these probability clouds can have different shapes. I love this one. This is known as the F orbitals. Okay, it looks like it has fire or condom depending upon your perspective. And so these probability clouds do have shapes that you're looking at. So this is the modern day interpretation of the atom. And Max Born happens to be responsible for it. These matter waves are nothing more than the probability waves. These are just probability waves, just guiding the motion of these particles. They move at the speed of the particles. And this is the same interpretation of quantum theory, which splits into the Copenhagen interpretation as well as the Main-World's interpretation. Either interpretation is an extension of this interpretation, so no one questions.
And when he finally had that idea,
the interpretation of the probability waves,
he realized that he could merge the Schrodinger picture with the Bohr-Heisenberg picture to give us the modern-day theory of the quantum principle. In other words, the electron is a point particle, but you don't know quite where it is. And the probability of finding it at any given point is given by a wave, the Schrodinger wave.
So probabilities of where the particle is and what the particle is doing is embedded inside the wave. It's a mathematical wave. It's a probability wave. It's just a wave.
So we now have this
known as the Schrodinger wave.
Beautiful synthesis of waves and particles.
And that's it.
According to the quantum...
All right, I'm going to ignore this. All right, so moving forward. Einstein didn't like this interpretation. This was too hocus pocus. You didn't know where the particle was. You didn't know what the particle was doing. And then this is mathematically embedded into these weird waves, which were attached to the particles and then governing the behavior of particles, this and that. This sort of hocus pocus interpretation did not play well with Einstein, especially the probabilistic interpretation of reality at the atomic level. Einstein simply said God does not play dice. All right, as far as he was concerned, there was causality leading to the creation of the universe. As far as he was concerned, there was an electron inside the atom which occupied a definite position and occupied definite motion. And so he thought that it was going to be a matter of time before the more deterministic rules of physics was discovered. Until then, he decided that he was going to disprove the quantum mechanics the way it was. And he spent the rest of his life trying to do that.